Alright guys, we're going to go over some of the answers for your doodle notes here. Now remember, there isn't an exactly one right answer, but I just want to make sure that you've got an idea. So remember, it is intended for you to be able to like color it and make it look cute. Obviously not so cute here on this, but you get the picture. Alright, the first one. So these are all, the quantum numbers are just the way we describe the electron configuration. Okay, so we're going to be talking about our electron configuration. Oh, I forgot I have a dead spot on my screen here. Configuration here. You know what I'm trying to say here. Butchering it. Say config. Alright. Our electron configuration is like the word version of what we do. So remember, we're like 1s2, 2s2. Right? Go on and on and on. So the 1 in each of these, that is what's called our principal quantum number. They're the 1, the 2, the 3, whatever I typically call it is the energy level that it's found in. So, or you could just look to the period on the periodic table. And then the next page actually asks for that, so I'll leave it at that for now. Now the textbook definition is, this lets you know the size of the orbital. If the electron is in n equals 1, it is close to the nucleus. If it is n equals 6, it's far away from the nucleus. Okay, and that's because this, for instance, the spherical shape, remember, represents the s orbital. So this would be your 1s, your 2s, your 3s, 4s, 5s, 6s, and 7s. Alright, so that's one part of your electron configuration. It's going to tell you what these quantum numbers are. Okay, and n is our first one. Okay, it's that energy level. Now the angular momentum is just a real fun way that tells you what shape your orbital will be. So is it an S, a P, a D, and an F, or an F? Okay, it can be N, but or an F. Alright, so what they wanted you to see here is that this, obviously we've been saying the dumbbell is the P shape, okay? The P has many orientations, but that's the P shape. This is the S, this is the D, and this is the F. There's that dead spot on my screen again. Okay, so the S, P, D, and F orbitals. And that's L, or the angular momentum. Now the magnetic quantum number, the m sub L, okay, spin quantum number is m sub s, and the magnetic quantum number is m sub L. The easiest way to describe that is like, this is your x-axis, this is your y-axis, and this is like your z-axis. So in math, when you learn, let me draw it over here, your x and your y, remember z is like the axis that pops out at you. It's the third dimension. Okay, 1 dimension, 2 dimensions, and then there's your third. Okay, so it's hard to draw it in 2-dimensional space. Now the word version of it is the magnetic quantum number. There's a number associated with it. It's going to tell us if you look up or down or side or back and forth. So where to look, basically, based on orientation. So it's your orientation of the electron orbital. Now the spin number is probably the easiest to understand, right? In the basics, it's going to tell you how the spin is moving. So we say a positive 1 plus 1/2 plus for up, and a negative 1/2 for down. Okay, and if you look at your orbital diagram, it's wherever the last electron you placed is going to be. So obviously this is incorrect, because remember we had to go up to each one and then come back, so it's actually up, up, up if you're filling 3 electrons in what must be the P block, right? Because it's got 3 boxes, or 3 spaces, or 3 sub-levels, what we've been calling them. Okay, so it's going to tell us if we have an up spin or a down spin. Okay, down spin, up spin. and it's the last one. Okay, so because I had 3 electrons to fill, I went 1, 2, and 3. My third electron filled in this spot, I added an up, so it comes out as a positive 1/2. Now let's say I had 4 electrons in the p, I'd come back and do it down, then it'd be a negative. Okay, if this guy was here as my last, it'd be a negative. All right, but the example they gave us the last spin being up right here, so that's why it's a positive 1/2 for this one. Now for this part, they said, all right, let's say you've got phosphorus. So go ahead and look at your periodic table and find phosphorus. You're going to find that phosphorus in your periodic table is number 15. Okay, so number 15 means you have 15 protons and 15 electrons for an atom. All right, so we've talked about 15 being the atomic number. So phosphorus's atomic number is 15. So that means that we have 15 protons, and an atom would start with 15 electrons. Okay, but our quantum number, right, we said our principal quantum number is n. Okay, just like the last page. Okay, the first page told us, like, what is it? Now we're going to look at a specific example. So phosphorus, you can actually do the electron configuration. You're going to start at hydrogen every time. Remember, you go 1s2, 2s2, 2p, there's that dead spot again, oh, gosh dang, 6. All right, so if you look, that fills to neon. Okay, number 10, 2p6. Now you'd go from neon down to sodium, and you'd say energy level 3, S2, and then, I'm sorry, this isn't coming out in a straight line here, but you jump over to aluminum, and your energy level 3 of the P block, and you fill with 3 electrons. All right, so I'm going to rewrite that so it looks prettier here. All right, so again, 1s2, 2s2, 2p6, 3s2, 3p3. Okay, a little prettier, not that much. All right, now what they're saying is this is the shorthand. Now the shorthand for electron configuration is we're just going to think about when was the last time this atom had a stable valence shell. Okay, what you're going to do is you're going to try to find that last noble gas. Remember, so anytime you say P6, that's a noble gas. So 2P6 was actually your last noble gas, which is where you'll find neon. Okay, so how we would do the shorthand is we put neon in brackets, and then we line up the electron configuration after that. Okay, so everything that comes after that, which would be 3s2, 3p3, because in reality the only thing that matters is, sorry, I should have filled this one first, is where this last electron falls. So 3, I go up, 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 and I'm done. So 3p3. I need to just move my stuff down the bottom screen so it doesn't get so crazy like that. Alright, so I'm going to write the shorthand up here. Okay, so again, after neon, number 10, you go over to number 11, sodium, and you're in energy level 3, S2, which is that one, and then 3p3, which is that one. Okay, that's the shorthand electron configuration for phosphorus. All right, how do you figure out N? Remember, we figured out by looking at the period on the periodic table that it's found in. All right, so this 3, not either of the other 3s. So what they're saying is that this, the last one written, is going to tell me what energy level I'm in. Okay, whatever the last biggest number is, that's how I know which level I'm in. Oh, I forgot to write it right now. So that means my N is equal to 3. All right, now, how do you find L? Okay, L, remember, when we looked at the other packet, the L is going to be our angular momentum. Okay, and our angular momentum is essentially which shape are we taking. So what shape or what orbital, S, P, D, or F? Okay, now remember, principal quantum numbers, we're going to associate a number with each of them. So if it's an s orbital, it'll be 0, p orbital 1, d orbital 2, f orbital 3. Okay, just what shape it is. So we're going to look what's the last one that filled. It filled a p. That last electron was right here in this exponent. So once we filled the p, that means that we filled in the 1. Okay, so L equals 1. Okay, get principal quantum numbers. These numbers are going to describe our last electron and therefore our reactivity and so much more. All right, now how do you fill out your M sub L, or how do you figure it out? So your M sub L, remember, is your magnetic quantum number. Your magnetic quantum number is essentially what orientation is it going to be in. Okay, so what we have basically is each of these blocks represent a certain orbital. Okay, and every orbital based on where the electron is located, the last one, is going to tell us what number we pick here, and I'll tell you what that means. But so for remember the S block, if you look at the S, hydrogen, helium, lithium, beryllium, right? There's 2 electrons, an upspin and a downspin. So you have 1 box in the S block. Now in the P block, you have 6 groups. So you're going to have 3 bunk beds, remember, because each bunk bed can hold 2 electrons. There's snacks by the door. There's snacks by the door. Okay, so you've got 3 bunk beds, 1, 2, and 3, and you're going to fill like 1 up, 1 up, 1 up, come down and do the downs. Wherever your last one ends is what that's for. So this was S. I should have just written here. This is your P, your D, and your F. Now look at your D block. How many groups? There are 10. So if there are 10 people, it would take 5 bunk beds. 1, 2, 3, 4, 5. Look at your F block. Your periodic table will have 14 groups in your F block. Remember the lanthanides and actinides. 14 people would fit in 7 bunk beds. 1, 2, 3, 4, 5, 6, 7. Okay, now this is all based on probability of what's going to happen in terms of the orientation and where it lands with how many electrons are present in each state. So no matter what, the S is going to have the 0. Okay, I'll show you what the 0 means here in a second. Because every state, the 0 is the base. Like, that's the natural state that we tend to talk about. Okay, and that's your middle one. And if you go to the right one, it's going to be positive 1, the right 2, positive 2, and 3 would be 3, okay? And then the left, negative 1, negative 2, negative 1. Whereas S just has 1, just that one space, and it's because it's a sphere, it can't orientate differently anyways. So remember, this is your X, your Y, or your Z. Okay, and then combinations of others. Alright, so how do we figure it out? Again, we're looking at phosphorus. Our last box for phosphorus was up, up, up in the p orbital. So in the p block, we went up, up, up. So my last one ended here. So my M sub L is 1. Alright, my L was 1, and my M sub L is also 1. Alright, how do you figure out your M sub S? It's probably the easiest one of all. Like your last arrow, did it go up or down? If it went up, it's a positive 1/2. If it went down, it's a negative 1/2. And this means spins up. This means spin down. Oops. Down. My goodness, I'm going to erase that and try again. Did you get a snack, sweetie? Alright, so the way we can describe it is the last electron okay, and remember we went, these were our boxes for phosphorus, and we went up, 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 there's an arrow up. So that electron being up means we had a spin up for this one. Positive 1/2 spin up, okay? Alright. Okay, so orbitals come in 4 different shapes. Learn about those shapes below by answering the questions, drawing the electrons in the box, and writing everything you know about each orbital. So for the S subshell, right, if we've got the S subshell, and we're looking at this, this means we just have a single S orbital, right, because S only has one subshell. Okay, yep. And then how many electrons can fit? You can fit 2 electrons in the S orbital. Okay, so you go 1 up, 1 down. That box represents your 1 subshell. And this is your S. Now your P. Your P subshell. This is if you have a single p orbital here. Okay, single p here. There are other options. Okay, this is just a single p orbital here. Now, if you have a 3p orbital, it can hold many more electrons. Okay, because what can actually happen is you can have it on the X, you can have it on the Y, and then you can have it on the Z. Okay, and if each one of those holds 2, those are 3 subshells, and it can hold a total of 6 electrons. So you go 1 up, 1 up, 1 up, and then down, down, down. Now your D, remember it has 10 groups. It can hold 5 subshells. Okay, so 5 subshells, and it can hold 10 electrons. All right, so there are 2 ways a single d orbital could look. Okay, so remember I said the F example we gave you on the board looked similar to the D, but it had 2 pancakes rather than the 1. Okay, that's the only difference, is this F actually has 2 pancakes, whereas the D only had 1. Okay, there's a lot more complex to it. It's got those shapes, and then it can exist on multiple axes. But these are your 5 subshells. Okay, and so remember with 10 electrons, you're going to go up, 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 5, 6, 7, 8, 9, 10. Okay, so that's how much can be held in the d orbital. Now the F subshell, remember there were 14 subshells, 14 electrons possible. Right, that's how many groups there are in the F subshell, which means there are 7 subshells. Because you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's all 14 of my electrons. All right, these are the 2 ways a single F subshell, or F orbital, I should say, all right, next page. I feel like we should number these. Technically, this would be my 3rd page here. So let's move on to the 4th page, where you actually start talking about electron configuration. All right, so now we're going to tie all those quantum numbers into what it means in terms of electron configuration. All right, so that 2 that we see here is your energy level. N equals 2, which is the period on the periodic table. All right, P is telling me my orbital, which tells me the shape. Right, is it a dumbbell, a sphere? It'd be S, P, D, or F. And again, the way you can tell that is where your last electron lands. Now this, the 3 exponent, is the number of electrons in that subshell. Alright, so if you look here, this is where I was saying we tend to not jump into the d orbitals, and the reason is we don't do it first semester right now. We're going to do it second semester. It's because when we start, we're going to go hydrogen is 1, helium 2. Maybe I'll just grab my highlighter, see if this works. So you go hydrogen, helium, and then that dead spot again. Okay, we're not. Helium, okay, that's 2. Lithium 3. Beryllium 4. Okay, so we are energy level 1 to 2 to 2. Jump over neon, and then over to here is 3. Okay, and then what actually happens is, see in your periodic table, technically the D block's there, but in reality the D block's down a bit. Okay, if it were written correctly, it would scoosh it down, and you would go back up to energy level 3. Okay, so your D block here, this is your D block, it's actually energy level 3 of the D block, not 4. Okay, and then you come back, when you get to the P, you have to jump back up to the 4 and fill a 4 to 4 PS. Okay, and then you come back to 5, fill 5S 1, 2, and you go 4D 1 through 10, and then you jump over to 5P. Okay, so you can actually use your periodic table really handy, but you just gotta remember that the D jumps down. Okay, remember, and technically the lanthanide actinides fall here, but you actually jump up a level on that one too. So the D block jumps up a level and the F block jumps up a level. If you remember that, everything else is just fine. Okay, so for this one, we're filling nitrogen. Alright, so if we find nitrogen in our periodic table here, nitrogen is right here, number 7. Okay. Oh, actually, they filled nitrogen. Wait, what? Yeah, no, they are doing nitrogen. Okay. So nitrogen, you're always going to start with hydrogen. So 1s1, 1s2. Okay, so 1s2 right here. Alright. You passed your first checkpoint. Okay, now 2s1, 2. You passed your second checkpoint. So check 1, that box, that little flag, and this is your check 2. Now 2p3 goes 2 of the p, 1, 2, 3. This is where your last electron lands. Okay, so not too bad. Alright, just for nitrogen. One thing I want to show you here, if we look at our highest energy level, it's 2. Okay, so energy level 2 and 2. How many electrons do we have? We have 2 and 3. Now what we'll find later is that we'll actually find that nitrogen has 5 valence electrons. So it goes 1. We'll talk about that again later, but that's because 2 plus 3 is 5. Okay, we also know the highest energy level is 2, right? Our quantum number for this nitrogen. Alright, so let's look down here, next page. Alright, so there's some questions here we're going to answer. How many orbitals are there in the p subshell? Okay, so orbitals in the p subshell. There are 3. Okay, ready? 1, 2, 3. 3 orbitals in the p subshell. The subshell would be this whole thing. Okay, and 1, 2, 3 orbitals present. Now sometimes they'll just say the p orbital, and that just means that that's the shape. Okay, but each one of these is an orbital as well. Okay, so there are 3. Okay, and they're like rooms that share electrons. All right, each one of these boxes over here is an orbital. Okay, and it's either going to be arrows in it up, down, and it'll tell us the orientation. Okay, and with the P, remember we're going to have one that's up and down, one side to side, and one front to back. Okay, up, down, side to side, front to back. That's what those technically represent. Like your X, your Y, and your Z. Alright, now shells is all of the electrons in a specific energy level. Okay, so like let's look at, is there a certain one they want us to do for this one? So I'm not sure what they wanted us to do with this. So all electrons, so we'll say all electrons in last energy level, or say in any, and the last energy level will give you the valence electrons. So like if we were to look at, I think it'd make sense to give you a specific example. So if we were to look at something in the 4F, I don't like that. Let's do something in the 4S. Okay, so say that there's a 1 up, 1 down. Okay, so in the 4S, and then we had your 4P, like these are just the highest energy listed. There could be 3s and 2s, obviously there would be, but you've got this present. So your valence electrons would just be those 3, the highest energy level. I'll talk more about that. I don't think that made enough sense. I need to give you a specific example here. Alright, what they want you to do down here is, what is a subshell? So a subshell is all of the electrons that can be found in a specific orbital shape, so like all of the P or the D, for example, but at a certain energy level as well. So like 4P, how many electrons are actually there? This is a subshell. And this subshell has 3 orbitals. So all electrons within a certain or a specific orbit shape and energy level. Alright, and then that's the key. Alright. So I would like to look at a specific example quick. Let's look at, for example, let's look here. Let's do an electron configuration for somebody. Let's do one for, I'm going to erase this here so I can have some room to do it. Let's look at phosphorus again because we looked at it so frequently on the other side here. If we look at phosphorus, alright, phosphorus is right here, number 15. Okay, so phosphorus, right, we always start at 1, energy level 1, so 1s2, 2s2, 2p6. Remember, we're just counting from 1 to 2 to 3 to 4, and I'm in 2, and I'm in the P block, sorry, S block, oh, S block. Now I'm in the P block, 2P, 1, 2, 3, 4, 5, 6. You got me to the end, so that takes me to neon. Now I jumped under the 3rd energy level, and I'm in 3S, 1, 2. Okay, jump over energy level 3 of the P orbital, 1, 2, 3 to fill to get there. I want to show you the correlation between this and our Bohr model. Okay, if we were to draw the Bohr model for phosphorus, what's going to happen is you have 15 protons and 15 electrons, right? So you have your I'm just saying nucleus here, but right, remember we said you can tell how many rings it's going to have on the Bohr model by which period it's in, okay? So if it's in the third energy level, it's going to have 3 rings. Okay, we're just pretending this is the nucleus, right, with all the protons, all the neutrons. Okay, but if we have these, the first shell can only hold 2, remember, so 2 of the 15. And now the next shell can only hold 8, so 8 plus 2 is 10. So I'm going to have 8 on this shell. Okay, now I've got 8 and 2, so 10. So now the next energy level can hold 1, 2, 3, 4, and 5. Okay, so we've looked at in the past how that would actually mean that we have 1, 2, 3 locations that want to pair up. Or in other terms, this valence shell, the outer shell, has 1, 2, 3, 4, and 5 electrons present. So it has 5, wants 8. Okay, so that's why, this is group 15. We usually say 5 valence electrons for everybody in this group. Okay, so phosphorus had 5 valence electrons. Let's look at what that means when we look at the electron configuration. Okay, energy level 1 has 1, 2 electrons. Energy level 2, right, these two, has 2 plus 6. Energy level has 1, 2, 3, 4, 5, 6, 7, 8. 2 plus 6. Energy level 3 has 2 plus 3. It has 5, just like we said, 1, 2, 3, 4, 5. Okay, so this highest number, and then you add them together because there's 2 in the 3. Sorry, I didn't circle the 3. 2 plus 3 tells me there's 5 valence electrons. Alright, so that's how the correlation between the Bohr model, which is this guy down here, and the electron configuration works.